Hi guys, so today we're talking about integration and long division. Okay, so today is March 26th, 2020. All right, okay, so here we go. Find the integral of 1 over 4x minus 1 dx. Okay, so this doesn't look like any of the integration rules that we've learned. Okay, so what else could we do? Well, we could go to integration by substitution. Well, what should we try to let u be? Okay, so we know if we take the derivative of this, we would pick up a 4 and then a dx, right? Okay, so if we let this be u, because the derivative of negative 1 would be 0. If we let u be this, u equal 4x minus 1, then du would become 4 times dx. Okay, so that's what we're gonna make UB, all right? So now what we need is a 4 with the dx, right? Because we don't have that right now. But from previous lessons, you realize, oh, we can put it, right? As long as we rewrite it with multiplying by 4 and also 1/4, okay? Now, again, you can only do this with constants, okay? All right, so this is equal to the integral of 1/4 times 4 times 1 over 4x minus 1 dx. And the 4 here, along with the dx, is going to make up my du. And then this part right here is going to be my u. So this 1/4 is going to get pulled out. So 1/4 times the integral of 1 over u du. And we recognize that as one of our integration rules, right? Okay, or antiderivative rules. So this becomes 1/4 times the natural log of the absolute value of u. Now this is an indefinite integral, right? So we're finding antiderivatives, okay? So this is the antiderivative of this original function. So we don't know, remember, that we could have a constant. So we need to remember to put plus c, the constant, okay? So then the final answer would be we got to replace the u, all right, with what it's equivalent to, which is 4x minus 1. So our final answer to this would be 1/4 the natural log of the absolute value of 4x minus 1 plus your constant c. Okay, and that's the first example, right? All right, so for example 2, what I want to talk about is in all three of these examples for the first page, we're gonna wind up letting u be the denominator, and this is why. The derivative of this denominator will become the numerator times dx, or we can fix it so it is like we did the previous problem, okay? All right, so this time we're gonna want to let u be this denominator, because if you look at this, if we take the derivative of this, we would get 3x squared plus the 1 and then dx, all right? So we're gonna let u equal x cubed plus x, and then du would be 3x squared plus 1 times your dx, all right? So this is going to equal the integral of, and this is your u, and this together makes your du. You don't need to fix anything for this one, right? So this becomes 1 over u du, which we know from the previous problem and our integration rules, that this is the natural log of the absolute value of u plus c. Well, what's u? We got to replace u with what it's equal to. Well, it's x cubed plus x. So this winds up being the natural log of the absolute value of x cubed plus x plus your constant c. And that's the answer to example 2. All right, for example number 3, we want to find the integral of secant squared x over tan x dx. All right, and you notice again, okay, if these are all quotients that I'm giving you, because that's when we're going to need to use this long division idea, okay? We haven't even done the long division yet, okay? But if we're looking at these problems when you have a quotient, all right, look and see, okay, if you let the denominator be your u, okay, is the numerator the derivative of the denominator, okay? All right, so if we let u be tan x, du would become secant squared x dx. Okay, so we have our u and we also have our du, right? Okay, so this becomes the integral of 1 over u du. And so we can, so these all, a lot of times these will take on this form, right? Where if you take the derivative of the denominator, you pick up the numerator, okay? All right, so this would be the natural log of the absolute value of u plus some constant c, and then that would become natural log of the absolute value of tan of x plus your constant c. And that's the integral of secant squared x over tan x dx. All right, let's go to the next example. For example 4, we want to find the integral of x plus 1 over x squared plus 2x dx. All right, if you look at this, okay, what happens if we take the derivative of our denominator? Well, we get 2x plus 2. So we don't get x plus 1, but we get 2x plus 2. Well, 2x plus 2 is just a multiple of x plus 1. And that's what we have to recognize on this one, okay? We're going to have to fix it a little bit, okay? So we're going to let u be x squared plus 2x, and then du would be equal to 2x plus 2 times your dx, okay? Now, if you look at this, we could factor out a 2 out of these, right? So our du is really 2 times x plus 1 dx. And here we have our x plus 1 and our dx. That's our numerator, right? Okay, so we need a 2. So we can multiply by 2 as long as we also multiply by 1/2. Okay, so we can set this equal to, this is equal to the integral of 1/2 times, and I'm going to put the 2 in the numerator, 2 times x plus 1 over x squared plus 2x, and then dx. So this x plus 1 dx, actually the 2 times x plus 1 dx, okay, these three terms right here, okay, these three things make up your du, and this 1/2 can come out. So this would be equivalent to 1/2 the integral of, and this is your du, so it becomes 1 over u du. Okay, well, the integral of that is 1/2 natural log absolute value of u plus your constant c, and then that becomes equal to, and then that's 1/2. Our final answer would be 1/2 the natural log of the absolute value of x squared plus 2x plus your constant c. All right, and that's example 4. And up to this point, okay, we've been able to take the derivative of the denominator and we pick up the numerator, okay? So we always want to look for that when we see these quotients like this, okay? All right, so for example 5, we want to find the integral of x cubed minus 6x minus 20 over x plus 5 dx. So this is a problem where, okay, let's let u be x plus 5, the denominator, right? And if you do that, okay, you take the derivative of this and we get 1 dx. We're not picking up the numerator now, right? Okay, so what else could you do? Well, the other option is to do long division like we did last year in Honors Math 3, okay? And we're going to use an area model to do this, okay? So this is the area of our area model. Okay, this is the area. This is going to be one side, if you recall from last year. Okay, so we have x plus 5. That's going to be one side of our rectangle. Okay, and then we're going to add the first column. Okay. All right. So this area has to be the x cubed. Okay, so we go through x times what is going to give you x cubed? Well, it would be x squared. And then x squared times 5. This area down here would be 5x squared. And if you look, we don't have an x squared term. That means on this diagonal, because I'm going to need to add the next column, On this diagonal, all right, we have to have opposite coefficients. So this is 5x squared. This would have to be negative 5x squared. Remember doing this last year? All right. So what this makes, this diagonal would make 0x squared, okay? So x times what would give you the negative 5x squared? Well, it'd be negative 5x. So negative 5x. And then negative 5x times 5 would give you negative 25x. Okay, so if you look at our problem, we have negative 6x, right? So what would I have to add to negative 25x to get the negative 6x? Okay, so I'm going to add my next column. And what we would have to add is 19x. Because negative 25x and 19x make negative 6x, okay? So now we have to look at, okay, this side is x, this area is 19x, okay? What would I have to multiply x to get 19x? Well, it's positive 19, so we write plus 19. 19 times 5 would be 95. All right. And then we have to add, we have to fix this because this is our constant, right? But really for our constant, we have negative 20. So this is the remainder column. This is what I need to do to fix it, right? So it's not a full column. All right. So what we need negative 20. Okay. So what needs to go right here is negative 115. Now, why negative 115? Because this diagonal needs to add up to be the negative 20, right? And 95 and negative 115 make negative 20. So the diagonals always have to add up to give you the term that you have, okay? All right, so that means we can rewrite this problem right here. Now, one of the reasons that allows us to do this division is this is like an improper fraction. The degree for the numerator is higher than the degree of the denominator, okay? So the degree of the numerator is higher than the degree of the denominator. When that happens, you can do this long division. That's why when we try to take the derivative of this, we will not pick up the numerator, okay? Because we're going to drop this power by 1, right? All right. Okay, so rewriting this, we wind up with, okay, this is the integral of x squared, that's that term right there, minus 5x plus 19. And then our remainder is negative 115. So we're going to write minus 115 over x plus 5 and then dx. Okay, now we can break this, okay, into two integrals, one for this polynomial and then one for this, okay? So that's what we're going to do next, okay? So this becomes the integral of x squared minus 5x plus 19 dx, and then minus the integral of 115 over x plus 5 dx. All right. Now this 115 can get pulled out. So this is equal to the integral of x squared minus 5x plus 19 dx minus 115 times the integral of 1 over x plus 5 dx. Now, what happens if I take the derivative of this denominator? Well, the derivative of x plus 5 would be 1, right? And we get 1 dx. All right, so we're gonna do a u substitution for this. U is equal to x plus 5, and then du is equal to 1 dx. Okay, so I'm not going to integrate this yet until I turn this one into u, doing the u substitution, okay? So this is equivalent to the integral. And by the way, we do need this dx right here, okay? We can't leave it off. We need the dx, because what this is saying is everything between the integral symbol and the dx is what we're integrating. If you leave that off, we're continuing. We have like a double integral here. We're going to integrate this too, okay? So you don't want to do that. You want to put in the dx. If you wanted to, you could put parentheses around this and with the dx, and that would be fine, but you don't have to, okay? All right, so here we go. So this is still the integral of x squared minus 5x plus 19 dx minus 115, the integral of 1 over u du. Okay, now we're ready to integrate, okay? So this becomes x cubed over 3, that's just the power rule, minus 5x squared over 2. And I'm going to slide this up a little bit. Okay, and then plus 19x minus 115, and the integral of 1 over u is natural log absolute value of u, and then plus the c. Now we actually had a c here and a c here, and they just combined to make one giant constant at the end, okay? Now the only thing we have left to do is we need to replace this u with what it's equivalent to, which is x plus 5, okay? Now, you could leave it like this, x cubed over 3. Another alternative, another different way of writing this could be 1/3 x cubed minus 5 halves x squared plus 19x minus 115 natural log of the absolute value of x plus 5 plus some constant c, okay? And so I just want you to understand, like you could write this as 1/3 x cubed, or you could write it as x cubed over 3. Either way works for me, okay? It's just whichever way you prefer, okay? All right, and that's example 5, and we use long division to do it, okay? All right, for this next example 6, okay, we want to find the integral of x cubed minus 3x squared plus 4x minus 9 over x squared plus 3 dx. So again, you think, okay, let's let u be the denominator. Okay, so what's the derivative of x squared plus 3? Well, it would be 2x and then a dx, right? Well, that's not going to help me because the numerator has many more terms than that, right? And something else you need to realize here is that there's missing a term here in the denominator, right? So this is a candidate. This is one of the ones you'd want to try and use long division on, okay? All right, so there's a missing term down here in the denominator. There's no x term, right? So when we do this, the side of our rectangle needs to have an x squared plus a 0x and then plus a 3, okay? We need to replace any missing terms with a 0x, okay? Or 0 coefficients, okay? All right, so here we go. So the side of our rectangle is going to be x squared plus 0x plus 3. So this is going to have 3 rows in it, okay? So our first column okay, and then our highest power here is x cubed. So x cubed. So we have to look, okay, x squared times what would give us x cubed? And it would be an x, all right? And then x times 0x would give us 0x squared. And then x times 3 is 3x. So we have a positive 3x there, right? Okay, we're going to add our next column. So this is the x column. The next one's going to be our constant column. So we're going to add our next column. And this will be a full column. After this, it will be just the remainder column. Okay, so now this diagonal right here are x squareds. Excuse me. All right, and what we have up here is negative, excuse me. What we have up here is negative 3x squared. So this diagonal right here needs to be a negative 3x squared. Well, right here is 0x squared. So that means this one would have to be negative 3x squared to make it work. So this is negative 3x squared. And then you ask yourself, okay, x squared times what would give you the negative 3x squared? Well, it'd have to be minus 3, okay? And then negative 3 times 0x would give you 0x. And then negative 3 times positive 3, the area of this little piece right here would be negative 9, okay? And then you look, okay, do we need anything else, all right? So this is gonna be our remainder column, okay? Okay, so it's not a full column, okay? So this diagonal has 3 terms in it, right? We have 3x, 0x, and we have a missing term right here, okay? What we need is 4x. So we need this diagonal with 3 terms in it, right, to be 4x. So 3x plus 0x, what would this need to be? This would need to be 1x, right? So 1x or just x. All right. And then this diagonal right here is our constant, right? So we need it to be -9. Well, we already have -9. So that must mean this is 0. Okay. So this polynomial divided by this, by x squared plus 3, is x minus 3 plus what our remainder is over what our divisor, okay? All right, so we can rewrite this. This is equivalent to the integral of x minus 3. And then since this is positive 1x, it's plus, and that's our remainder. Our remainder goes over our divisor. So our remainder is x over x squared plus 3. And then dx. All right, so the next thing is, okay, we're gonna integrate this. This is just standard integration, and then we're gonna integrate this. So I'm gonna break it into two integrals. All right, so this is equivalent to the integral of x minus 3 dx plus, and once again, we need that dx right there, okay, plus the integral of x over x squared plus 3 dx. And if you notice on this one, okay, if we let u be x squared plus 3, we're going to pick up 2x dx. So you got to kind of do it in your head, thinking ahead. All right. So we're going to pick up this x and the dx, right? We just need a 2 with it. Well, we can fix that again, right? So we're going to let u, for this one, we're going to let u equal x squared plus 3. And then du would equal 2x dx. Okay, so then this would equal, okay, the integral of x minus 3 dx plus, we need a 2 up here, right? So this is the integral of 1/2 times 2x over x squared plus 3 dx. This 1/2 is going to come out. So this is the integral of x minus 3 dx plus 1/2 the integral of 2x dx makes my du, and the x squared plus 3 is u. So this is 1 over u du. And now we're ready to integrate. All right. So this is x squared over 2 minus 3x. There's a c here, but I'm just going to collect all the c's and write one c at the end of this, okay? And then plus 1/2 the natural log of the absolute value of u plus your constant c. And then the last step is to rewrite this, okay? Again, this is x squared over 2. That's the same as 1/2 x squared minus 3x plus 1/2 the natural log of the absolute value of x squared plus 3, and then plus your constant c, okay? And that's how you do a problem with long division on this one, okay? When you're missing a term. So I wanted to show you this example because we were missing a term when we were dividing, all right? Okay, and that's example 6. We have one more. Okay, for our last example, we have find the integral of 1 over x natural log of x dx, all right? So you look at this and go, okay, it's not polynomials like we've been working on, right? Okay, so what else could we let u be, okay? Or we're gonna need to use u, okay? What if we let u be x? Okay, so what's the derivative of x? Well, it'll just pick up a dx, right? So we'd have 1 over u. That wouldn't take care of this natural log of x, right? We wouldn't be able to get that natural log of x and rewrite it a different way, okay? What if, and this is where it's really helpful to know all your derivative rules and all your integral rules, because then it helps you to see this, okay? To see the antiderivatives and how to approach this, okay? What if, okay, we let u be x? That didn't work really. What if we let u be natural log of x? Okay, so what is the derivative of natural log of x? Well, it's 1 over x, right? Okay, so what if we rewrite this a little bit and we rewrite this as the integral of 1 over x times 1 over the natural log of x dx. And writing it this way really kind of helps you see it, okay? What if we let u equal the natural log of x? Then du, knowing our derivative rules, becomes 1 over x dx. So this 1 over x, along with the dx, make up my du, okay? All right, so here we go. So, let me put a line here and here. These two together, right, make up my du. And then this little part right here is this little part right here, this natural log of x is just your u. So this becomes the integral of 1 over u du. We know that one. We've been doing that one a lot today, right? Okay, so this is equivalent to, I'm going to come down here, right? This is equivalent to the natural log of the absolute value of u plus some constant c. Well, what's u? U is the natural log of x. So this is equal to the natural log of the absolute value of the natural log of x. So it looks like this, plus your c, okay? All right, so we didn't use long division on this one, right? So it's not just long division, okay? That's just one technique, okay? And what I want you to understand is a couple things you want to look at, okay? If you have a fraction, okay, and I want you to look at, okay, what if you let the denominator be u? Taking the derivative of that denominator, do you pick up the numerator, okay? So that's when you want to let your denominator be your u, okay? All right. The other thing is when you look at polynomials, okay, is the numerator a higher power than the denominator? If it is, then that's when you want to do long division, okay? So you want to see, is the degree of the numerator higher than the degree of the denominator? If it is, long division, okay? That's what should be going through your mind, okay? Just as your strategies of how do you integrate these and how do you find the antiderivatives, okay? All right, so that's the end of today's lesson, okay? I'm going to grab the assignment sheet and show you what you need to do for the assignment for this lesson, okay? All right, for this lesson, okay, today's date is March 26th, okay? And what I want you to do is the long division. I want you to do assignment 8-7, which is worksheet 8-7, okay? And I'll attach that in a Google assignment. And you guys, I'd really appreciate it. I really need you guys to submit your solutions, okay, your homework as a PDF, not as a JPEG, okay? And please use that CAM scanner. It's really nice. It makes it so much easier to see, okay? You don't have to be the best photographer, all right, to use that, and it just comes out so much cleaner, okay, and easier to read, all right? The JPEGs just come out as pictures, and then it just doesn't come out very well, okay? So make sure you save it as a PDF, all right? All right, thanks guys, and hope you have a wonderful day. I'm looking at the sunshine outside. I think I'm gonna go for a bike ride, okay? You guys take care, bye.